Subscribe our channel for more videos.
It was sitting there in the tropical sun like a gift, a perfectly intact Japanese bomber, abandoned, untouched, engine still gleaming. And when the American major climbed inside and saw what was and wasn't protecting those fuel tanks, he went completely silent. Because what he found didn't just shock him, it rewrote everything the Allies thought they understood about how Japan planned to win this war. It is January 31st, 1945, Clark Air Base, Luzon, Philippines. The jungle heat is already suffocating by mid-morning, and Major Frank McCoy is sweating through his uniform as he circles the most valuable piece of intelligence he has ever seen in his career. Tail number 76312. A Mitsubishi G4M Betty bomber sitting on its landing gear like it just rolled off the factory floor. No bullet holes, no fire damage, no crash scars. The crew had simply walked away from it when the Americans advanced. McCoy had spent years crawling through wreckage across the Pacific, piecing together the broken skeletons of Japanese aircraft to understand what the enemy was building. But this was different. This was whole. This was the real thing, completely intact, just sitting there waiting to give up every secret it had ever held. He began photographing it methodically, the cylindrical fuselage, almost 20 meters long, earning its Allied nickname immediately, the Flying Cigar. The wings stretching 25 meters tip to tip, the two massive 14-cylinder radial engines, each producing 1,500 horsepower, utterly undamaged. Everything pristine. Then he climbed inside. And that is the moment this story truly begins. Because what McCoy found inside those wings, or more precisely, what he did not find, would trigger one of the most important intelligence revelations of the entire Pacific War. It would explain why American fighter pilots had been calling this airplane the Flying Zippo for years. It would explain why the sky over Guadalcanal had turned into a crematorium for Japanese air crews. And it would expose a design philosophy so cold, so calculated, and so fundamentally different from anything Western engineers had ever chosen that analysts back home would spend months struggling to comprehend it. The fuel tanks were completely bare. No self-sealing rubber compound, no armor plating, no fire suppression systems, no protective coating of any kind, just thin aluminum skin, 2 millimeters thick, sitting between thousands of liters of high-octane aviation fuel and whatever the enemy decided to throw at it. In that single discovery, the entire story of Japan's air war in the Pacific suddenly made terrible, devastating sense. To understand why those tanks were unprotected, you have to go back to a conference room in Tokyo in September 1937, where a group of Japanese naval planners sat down and wrote a set of requirements that they believed would change the course of history. Japan's empire at that point stretched across enormous distances of ocean. Naval bases were separated by thousands of kilometers of open water. The Army had ground forces, the Navy had warships, but what Japan desperately needed was a bomber that could reach across those vast Pacific distances and strike targets that no other nation's aircraft could touch. The requirements they wrote down that day seemed almost insane. They wanted a top speed of nearly 400 kilometers per hour. They wanted a cruising altitude that would put the aircraft above most anti-aircraft fire. And they wanted a range, a combat range, carrying bombs or torpedoes of over 3,700 kilometers. Unloaded, they wanted it capable of nearly 5,000 kilometers. To put that in perspective, no bomber flying anywhere in the world in 1937 could come close to those numbers. American bombers, British bombers, German bombers, none of them were built to operate at those ranges. The Japanese Navy wasn't just asking for a good bomber, they were asking for something that had never existed before. The man handed the impossible task of making it exist was Kito Honjo, chief designer at Mitsubishi's facilities in Nagoya. Honjo was not a dreamer, he was a mathematician. He had studied at Junkers in Germany, absorbed European engineering principles, understood exactly how aircraft design worked at the molecular level of weight and thrust and fuel burn. And when he looked at the Navy's requirements and started running his calculations, he arrived at a conclusion that would haunt every man who ever climbed into a Betty bomber. The math simply did not work, not if you wanted the aircraft to survive. Here is the brutal arithmetic that Hanjo faced. To achieve the required range, the aircraft needed to carry nearly 5,000 liters of fuel. Aviation fuel weighs roughly 0.8 of a kilogram per liter. That means just the fuel alone accounted for nearly 4,000 kilograms of the aircraft's total weight before you added a single weapon, a single crew member, or a single instrument. The aircraft needed to be light, extraordinarily, obsessively, dangerously light. Now add what American bombers carried as standard equipment by the early 1940s. Self-sealing fuel tanks, which used layered rubber compounds that swelled on contact with fuel when punctured, sealing holes and preventing fires. Armored plating around crew positions, armored glass for the cockpit, fire suppression systems, protective bulkheads, redundant safety measures throughout the airframe. On a B-17 Flying Fortress, the combined weight of all that protection exceeded 1,000 kilograms. On a B-25 Mitchell, similar numbers. That protection was heavy, expensive, and from the American perspective, completely non-negotiable. For Hanjo's design, it was mathematically impossible. Every kilogram spent on protection was a kilogram stolen from fuel capacity. Every liter of fuel removed to compensate for the weight of armor was range sacrificed, and range was the entire point. The Navy had not asked for a safe bomber. They had asked for a bomber that could reach targets no one else could reach. And those two things, extreme range and crew protection, could not coexist in the same aircraft with the technology available in 1937. Hanjo made the decision. Protection would be sacrificed. The fuel tanks would be bare aluminum, no self-sealing compounds, no armor, no fire suppression. Every kilogram saved would go directly into fuel capacity and performance. The result would be an aircraft that could strike targets 6,300 kilometers away, the longest-ranged bomber in the world by an enormous margin. And the result would also be an aircraft that, if it ever took a single bullet in the wrong place, would become a flying torch. The Navy accepted these terms because they believed their strategic assumptions would protect their crews where armor could not. They assumed the war would be short and decisive. They assumed surprise and initiative would keep Betty formations out of range of enemy fighters for most of their operational life. They assumed the distances involved, the sheer impossibility of the ranges the Betty could cover, meant it operated in spaces where enemies simply could not reach it. Every one of those assumptions would be proven catastrophically, irreversibly wrong. The first G4M prototype flew on October 23, 1939, and it exceeded every performance requirement the Navy had specified. The designers had done the impossible. Speed beyond expectations, range beyond projections, payload exactly as needed. The aircraft entered production immediately, and by December 1941, roughly 180 Betty bombers were operational with the Japanese Navy.
Then December 7th arrived, and the world changed overnight. On December 8, 1941, the same morning that smoke was still rising from Pearl Harbor, 82 G4M Betty bombers lifted off from bases in Formosa, joined by older G3M bombers, and pointed their noses south toward the Philippines. Their target was Clark Field itself, the same base where McCoy would find tail number 76312 more than 3 years later, the same runways, the same tarmac, the same tropical heat. The attack achieved total surprise. The Japanese formation arrived at 12:35 in the afternoon, flying at 20,000 feet, high enough that American anti-aircraft guns simply could not reach them. 27 bombers dropped over 600 bombs across Clark Field's runways and facilities in a matter of minutes. Then the Zero fighters swept in at treetop level, their machine guns finding every aircraft the bombing run had left intact. Of 17 B-17 flying fortresses on the ground, 12 were destroyed. Nearly every P-40 Warhawk fighter was reduced to burning wreckage. In 45 minutes, American air power in the Philippines had effectively ceased to exist. The Betty bombers departed untouched. Not a single one had been scratched, because not a single American fighter had managed to get airborne in time to challenge them. They had struck from bases 460 miles away, a distance no American bomber could match at that stage of the war, and they had flown home without a mark on them. Lieutenant James Harrington, one of the surviving American pilots, watching from a bomb shelter as the Japanese formation withdrew north, captured the moment in his combat report. The precision of the attack, the altitude, the coordination, everything about it communicated a single message. These bombers could reach you from anywhere, and you could not reach them back. 2 days later, on December 10, 1941, the Betty demonstrated something even more shocking, something that shattered a belief that the world's navies had held since the first warship was built. A formation of G4M bombers, joined by older G3M Nells, found Force Z steaming through the South China Sea. The British task force was built around HMS Prince of Wales, one of the newest, most powerful battleships in the Royal Navy, displacing 43,000 tons of steel and armor, and HMS Repulse, a battlecruiser modernized in the 1930s. These were not small ships. These were the instruments of British naval supremacy in Asian waters. The Betty bombers carried Type 91 aerial torpedoes, each weighing 840 kilograms, with warheads designed specifically for shallow water operations. They came in coordinated waves, their approach geometry calculated to force the British ships into impossible evasion choices. No matter which way the helm turned, another torpedo track was already in the water ahead of the bow. Prince of Wales took at least 6 torpedo hits. The underwater explosions tore holes through the hull that flooded faster than damage control could respond. The battleship began listing, then capsizing, then descending. Repulse took at least 4 hits and followed her down. 841 British sailors died. Both capital ships, actively defending themselves with every anti-aircraft weapon they carried, maneuvering at maximum speed, had been sunk by aircraft alone in open sea. It had never happened before in the history of naval warfare. The G4M Betty bomber had just proven that the age of the battleship was over in 90 minutes. Through the first half of 1942, Betty formations struck targets across the entire Pacific with what seemed like impunity. Darwin, Australia, hit from bases 1,500 miles away, demonstrating range that exceeded Allied comprehension. Port Moresby pounded repeatedly from airfields across New Guinea's mountain ranges. Guadalcanal targeted from Rabaul over 600 miles of open water. The Betty's operational reach gave Japanese commanders strategic options that Allied planners struggled to counter, because Allied fighters based at forward positions often lacked the range to intercept bombers departing from such distant bases. Japanese forces could attack at will. Allied forces could barely retaliate. This was exactly what the designers had intended. This was the design working perfectly. But everything that made the Betty extraordinary in those early months, all the performance that Hanjo had purchased through his brutal weight calculations, rested on a single condition. The aircraft had to stay out of reach of Allied fighters. The moment that condition changed, every number in Hanjo's equations inverted. Every advantage became a liability. Every kilogram saved by stripping out protection became a kilogram of death sentence carried silently in every mission. The change began in mid-1942 when American fighter strength started recovering from the catastrophic losses of the war's opening months. Better fighters began arriving, the F-4F Wildcat giving way to more capable aircraft, pilot training evolving, combat experience accumulating, and Betty crews began reporting something that the losses confirmed in brutal statistics. They were dying, not occasionally, systematically, catastrophically. The horror became undeniable on August 8, 1942. 23 G4M Betty bombers from the 4th Air Group departed Rabaul and turned toward Guadalcanal. American fighters intercepted the formation over Tsavo Island. In the engagement that followed, 18 of the 23 Betty bombers were shot down. Approximately 120 Japanese aviators died in that single engagement, the worst single mission loss the G4M would suffer in the entire Pacific campaign. Fighter pilots reported the same observation after every engagement. You hit the Betty anywhere at all along the fuselage, anywhere in the wing structure, and the result was always the same: a flash of orange, a billowing cloud of black smoke, and then pieces of what had been an aircraft and a crew raining down into the ocean. 2 or 3 rounds, that was all it took. 2 or 3 rounds from a machine gun, finding those unprotected aluminum tanks, puncturing them without any rubber lining to swell and seal the hole, and the fuel would spray into hot engine compartments, or ignite against exhaust stacks, or detonate from tracer rounds, and the entire aircraft would simply cease to exist in any meaningful structural sense. It would become a fireball. The fireball would fall. The crew would not survive, because there was no surviving a fire that size in an aircraft that had no compartmentalization of its fuel system, no suppression systems to fight the flames, no armor to buy the crew even a few extra seconds. The Betty earned its nicknames through repetition: Flying Cigar, One-Shot Lighter, Flying Zippo. These were not invented by clever staff officers sitting in briefing rooms. They were coined by pilots who had watched the same thing happen over and over until it seemed almost routine. Hit them anywhere in the wing or fuselage, and they explode. Always. Lieutenant James Thomas, commanding VF-17 flying F-4U Corsairs from Guadalcanal by October 1942, described it with the flat, direct language of a man who had seen the same result too many times to feel surprise. His pilots actively hunted Betty formations, recognizing them as among the most vulnerable targets in Pacific skies, not because the Betty was poorly designed, not because Japanese pilots were bad, but because an aircraft with unprotected fuel tanks in combat with fighters with machine guns and cannon was an aircraft already on fire. It just hadn't been lit yet.
The first real intelligence breakthrough came when Australian forces overran Japanese airfields at Buna in Papua New Guinea in November 1942. Among the abandoned aircraft, Allied technical intelligence teams found Betty bombers in various states of damage, and for the first time began systematic examination of the fuel tank arrangement. What they found confirmed what the pilots had been reporting: 8 fuel tanks, 4 in each wing, positioned in the wing's center section, the thickest part of the structure, designed that way to maximize capacity. Completely unprotected bare aluminum, no rubber lining, no coating, no armor. Identical across every aircraft examined. This was not a field modification or a batch defect. This was the standard design. American engineers calculated the weight saved by this choice: over 500 kilograms per aircraft. 500 kilograms that translated directly into fuel, into range, into the numbers that made the Betty what it was. 500 kilograms that also translated directly into the death of crews, mission after mission, whenever American fighters found them. The comparison with American aircraft was almost cruel.
The B-17 Flying Fortress featured self-sealing tanks from the B-17C model onward, standard production, non-negotiable. Armor plating protecting pilot and co-pilot seats, armored bulkheads throughout the fuselage, armored glass at the bombardier position, protective shields at waist gunner positions. The B-25 Mitchell, introduced in 1941 and comparable to the Betty in size and role, carried roughly 2,000 kilograms more in empty weight than the Japanese bomber. That weight difference was, in large part, the weight of keeping the crew alive. American wartime studies quantified the value of that weight with statistical precision that is uncomfortable to read even now. Body armor reduced thoracic wound fatalities from 36% to 8%, more than a 75% reduction. Self-sealing fuel tanks reduced fire-related casualties by similar margins. Aircraft with protected fuel systems showed survival rates 3 to 4 times higher than unprotected aircraft when sustaining combat damage. 3 to 4 times. For the crews climbing into those aircraft, that number was not an abstraction. It was the difference between coming home and burning over the ocean. American doctrine had concluded that trained, experienced air crews represented assets more valuable than the aircraft they flew. They could not be mass-produced. They could not be replaced quickly. Every experienced pilot, navigator, or bombardier that survived a mission and returned home carried knowledge that made every subsequent mission more effective. The weight penalty of protection was not a cost. It was an investment in the war's most irreplaceable resource, human experience. Japanese doctrine had reached a different conclusion. The Betty's design did not reflect indifference to crew lives in any simple or cynical sense. It reflected a calculation, a genuine, mathematically grounded calculation that mission capability was worth more than crew survival, because the missions would be decisive before attrition became unsustainable. The war would be short, the advantages would be overwhelming, the enemy would be forced to terms before Japanese losses could accumulate to catastrophic levels. The war was not short, the advantages were not overwhelming, the enemy was not forced to terms. By mid-1943, Japanese engineers knew that something had to be done. Starting with the 663rd aircraft produced, 30mm rubber sheets were installed beneath wing surfaces over the fuel tank areas. The word installed makes this sound more comprehensive than it was. These were not true self-sealing tanks. They were rubber panels attached to the exterior of the existing aluminum construction, a compromise measure that added minimal weight while providing limited protection against fuel leakage from small-caliber rounds. They could slow a drip. They could not stop a fire. They could not prevent the detonation of fuel vapor when tracer rounds crossed the wing. They reduced top speed by 9 kilometers per hour and cut maximum range by 315 kilometers, and they made essentially no measurable difference in crew survival rates. The G4M Model 3, introduced in October 1944, finally incorporated actual self-sealing fuel tanks, the real thing, the layered rubber compound that Western Air Forces had used from the late 1930s. The modification required reducing total fuel capacity from 4,700 liters to 4,400, and the resulting loss of range was staggering. Maximum range dropped to 3,640 kilometers, a loss of over 2,000 kilometers compared to the original Model 1. The aircraft that had been defined by its extraordinary reach suddenly couldn't reach anywhere near as far. And only 60 to 91 of these aircraft were completed before the war ended. The modification that might have saved thousands of Japanese lives built into aircraft from the beginning with 1937's technology, because the self-sealing compounds existed then and were being used by every other major air force, arrived 8 years late, in quantities too small to matter, at a point in the war when American air superiority was so total that no amount of fuel tank protection would have changed the strategic equation anyway. And yet, the Betty kept flying.
It had to keep flying because Japan had built roughly 2,400 of them and had no replacement ready, and the war needed aircraft regardless of what happened to the men inside them. The most famous single mission in the Betty's history came on April 18, 1943, and it demonstrated both the aircraft's fatal vulnerability and the extraordinary capability of the intelligence operation that had been watching it for months. American codebreakers intercepted Japanese communications indicating that Admiral Isoroku Yamamoto, Commander-in-Chief of the Combined Fleet, architect of Pearl Harbor, the single most important military figure in Japan's war at sea, would be flying from Rabaul to Bougainville on an inspection tour. The message included the exact route, the exact timing, the exact composition of the escort. It was the most valuable piece of operational intelligence the Pacific Theater had produced. 16 P-38 Lightnings from the 339th Fighter Squadron were assigned to intercept. The mission requirements were staggering. They would fly over 400 miles at wave-top height to avoid Japanese radar, navigating across open ocean with no landmarks, maintaining strict radio silence, and arrive at a precise intercept point at a precise time, a window measured in minutes over a dot of coastline in the middle of the Pacific. Any deviation in navigation, any error in timing, any mechanical failure, and Yamamoto's aircraft would pass by unseen. They departed Guadalcanal at 7:25 in the morning. They flew for over 2 hours at 50 feet above the ocean's surface, engines pushing them through the salt air in total silence, except for the roar they could hear but could not reduce. Then at 9:34, exactly on schedule, 1 minute ahead of the calculated intercept time, they saw the formation. 2 Betty bombers at low altitude, 6 Zero fighters as escort. Captain Thomas Lanphier and First Lieutenant Rex Barber broke from the formation to engage the bombers, while the remaining Lightnings held off the Zeros. Barber engaged the lead Betty, the one carrying Yamamoto, and his guns found the wing, the fuel tanks, the bare aluminum skin over thousands of liters of aviation fuel, with nothing between them and the rounds coming through. The aircraft exploded into fire and crashed into the jungle. Yamamoto's body was recovered the following day. He had survived the crash, but died from his wounds. Japan lost the man who had planned Pearl Harbor, executed the early campaigns, and represented the strategic genius at the heart of its naval war. He died because the aircraft designed to carry him to his inspection tour was built to prioritize range over the lives inside it.
The tragedy of the Betty's final operational chapter is almost too dark to describe without stopping. By early 1945, the strategic situation had deteriorated so catastrophically that Japan was reaching for any weapon that might alter the arithmetic of defeat. The result was the Oka, a rocket-powered piloted aircraft carrying a 1,200-kilogram warhead designed for one purpose only. The pilot pointed it at an enemy ship and died with it on impact. The Oka could not fly to its target on its own power. It had to be carried there by a mother aircraft. That mother aircraft was the Betty bomber. 18 G4M bombers took off from Kanoya Air Base on March 21, 1945, each one carrying an Oka weapon hanging beneath its fuselage. The weight and drag of the Oka reduced the Betty's already compromised performance further. Slower, less maneuverable, utterly unable to evade. Each bomber carried a crew, and each Oka carried one pilot who had volunteered to die. American radar detected the formation while it was still 100 miles out. F-6FF Hellcats from USS Hornet were scrambled immediately and reached the Japanese formation long before it could approach the 20-kilometer release range that the Oka required. In the engagement that followed, the outcome was not a battle. It was a systematic, unavoidable destruction. The Betty bombers could not evade. They could not accelerate. They could not survive. One by one, they exploded and fell into the ocean.
Not one Betty survived to reach release range. Not one Oka was launched. Not one American ship was threatened. 137 bomber crew members died. 15 Oka pilots, men who had come to the aircraft already prepared for death, who had written their final letters and accepted their fate, died without even the chance to complete the mission that was supposed to give their deaths meaning. They were killed before they could be killed on their own terms, because the aircraft designed to carry them to their targets could not survive long enough to release them. The Betty bomber, by the end, was kimming Japan's aviators in service of missions that could not succeed. The range that defined it meant nothing. The performance that had been purchased with crew lives meant nothing. An aircraft that cannot survive to reach weapon release range might as well not exist. The production numbers tell the quantitative story. Approximately 2,400 Betty bombers built across all variants over 4 years of war. The G4M Model 1, roughly 1,172 aircraft, carrying the original bare aluminum tanks with that 6,000-kilometer range and that absolute total absence of protection. The Model 2, approximately 1,142 aircraft, actually increasing fuel capacity to 6,490 liters, extending range even further, still retaining the fundamental vulnerability that had been writing crew death sentences since August 1942. The Model 3, with its self-sealing tanks, 60 to 91 aircraft, arriving years too late. By August 1945, when Japan's surrender ended the war, only a handful of operational Betty bombers remained. The aircraft that had numbered in the hundreds in 1942 had been reduced to dozens by attrition that no production rate could match, because the attrition was not random combat loss, it was structural. It was built into the aircraft itself. Every Betty hit anywhere in the wing or fuselage burned, always. The math of that reality, multiplied across hundreds of missions over 4 years, had consumed the fleet. The casualty statistics among Betty crews exist in fragments and approximations because Japanese record-keeping in the war's final years was incomplete and much of what survived was destroyed in the post-war chaos. What is certain is that thousands of Japanese air crews died in Betty bombers. Thousands of men who understood the danger, who had heard the nicknames, who had watched friends leave and not return, who knew exactly what the bare aluminum tanks meant for their survival odds, climbed into those aircraft anyway, because they were ordered to, because military culture demanded it, because in the Imperial Japanese Navy you flew the aircraft they gave you, and you did not ask for protection that the design philosophy had already decided you did not deserve. Former Flight Petty Officer Masao Wato, who completed 28 combat missions before transfer to training duties, an extraordinary number of missions in an aircraft with the Betty's loss rate, described it with devastating simplicity. The Betty was a magnificent aircraft that asked them to die for its range. They flew it because they were ordered to fly it. They died in it because that was what it was designed to make them do. Read that again. An aircraft designed to make its crews die. Not intended to, not accepted as a risk. Designed, through deliberate engineering choices, to prioritize a performance number over the lives of the people inside. When Major McCoy climbed into tail number 763-12 in January 1945 and saw those unprotected tanks, his hands trembled, not from fear, but from the weight of the realization. This was not an oversight. This was not a wartime shortcut taken in desperation. This was the aircraft exactly as it had been designed, exactly as it had rolled off the Nagoya production line in 1941, exactly as thousands of Japanese aviators had climbed into and flown across the Pacific for 4 years. The tanks were bare because Kido Hanjo had chosen to make them bare. The choice was deliberate, calculated, and in its own mathematical terms, correct. The Betty could reach targets no other bomber in the world could reach. It had done exactly what the specifications required. The crews had paid for that range with their lives, and they had been paying since August 1942. And they kept paying until the very last days of the war. And the aircraft had never been modified quickly enough or comprehensively enough to change that fundamental equation, because the modification that would have helped, self-sealing tanks, would have cost the range that was the entire reason the aircraft existed. The final image of the Betty bomber is both haunting and fitting. August 19, 1945, 4 days after Emperor Hirohito announced Japan's surrender over the radio, 2 G4M bombers departed at Sugi Airfield, painted white with green crosses indicating peaceful intent. Their call signs were Bataan 1 and Bataan 2, named deliberately for the peninsula where American forces had surrendered to Japan in April 1942, one of the most devastating American defeats of the entire war. The aircraft carried Japan's surrender acknowledgement in the war's final days. The bomber that had destroyed American air power in the Philippines in the war's first hours carried Japan's acknowledgement of defeat in the war's final days. The aircraft that symbolized Japanese air power's extraordinary reach now symbolized the consequences of the assumptions that reach had been built upon.
McCoy's report on tail numbers 763-12, classified secret and distributed to all Allied air forces, ran to dozens of pages of technical specifications and engineering analysis. But its essential finding could be summarized in a single observation that the pilots had already known for 3 years, from the first moment they watched a Betty take 2 rounds in the wing and disappear in a column of flame. The aircraft had been designed brilliantly to achieve specific goals. Those goals simply did not include bringing Japanese crews home alive. In that single fact, in the deliberate, calculated, mathematically grounded decision to leave those tanks bare, lies the complete explanation of why Japan lost the air war over the Pacific. Not because Japanese pilots were inferior, not because Japanese aircraft were poorly built, not because Japanese engineers lacked skill or ingenuity. Kiro Honjo was as talented an aeronautical engineer as any man designing aircraft anywhere in the world in the late 1930s. He delivered exactly what the specifications demanded, and the specifications demanded a miracle, and he produced one. But the specifications were built on assumptions, and the assumptions were wrong. And the men who paid for those wrong assumptions were not the planners who wrote the requirements in 1937. They were the flight crews who climbed into bare aluminum flying fuel tanks in 1942 and 1943 and 1944, and flew out over the Pacific knowing the statistics, knowing the nicknames, knowing exactly what a few rounds from an American fighter's guns would do to the wings of their aircraft, and flew anyway. American designers answered the fundamental question of bomber design by deciding that crews were worth protecting, even at the cost of performance. They built aircraft that were slower and heavier and shorter ranged because they decided that bringing people home mattered more than the extra miles of reach. Japanese designers answered differently, and both answers produced aircraft that worked perfectly within their design parameters, and the war revealed which design parameter turned out to matter more. In the end, the nation that valued crew survival built an air force that could sustain operations indefinitely, absorbing losses, replacing aircraft, accumulating experience, growing stronger with every month. The nation that accepted the systematic sacrifice of experienced air crews for performance advantages built an air force that burned itself out in less than 2 years, consuming irreplaceable men in missions that grew more hopeless with every aircraft that fell. Major McCoy spent 3 weeks with tail number 76312 before his team finished their analysis. When they were done, they had documented every system, every measurement,
every design choice that the Betty's engineers had made. The report went out to every Allied Air Force in the Pacific. But by January 1945, the report was almost redundant. Every American fighter pilot who had ever fired his guns at a Betty formation already understood the essential conclusion. Those tanks were unprotected because the men who designed the aircraft had decided something. They had decided that 6,000 kilometers of range was worth more than the lives required to purchase it. They had written that decision into the aluminum skin of over 2,400 aircraft, and thousands of young Japanese aircrews had climbed into those aircraft and flown out over the Pacific and paid the price for a decision they had no part in making. This is not just a story about an airplane. It is a story about what happens when the people who design weapons and the people who die inside them are separated by assumptions that no one tests until it is too late. It is a story about the difference between a design requirement and a death sentence, and how thin that line can be when the wrong assumptions are built in at the beginning. The Betty bomber was not a failure. It was, in its terrible way, a masterpiece. It just wasn't designed to keep anyone alive. If this story hit you the way it hits everyone who learns it for the first time, drop a comment below. Tell me what you think about the choice Hanjo made. Was it a decision forced by impossible requirements, or was it something darker? And if you want more stories about the hidden engineering decisions and forgotten human costs behind the most famous aircraft of the Second World War, subscribe right now, because we have barely scratched the surface of what these machines and the people inside them left behind.